Okay, so in this video, what I'd like to have a look at are the Laplace transforms of discontinuous functions. So that's when you have a function that will be on or be active within a certain time domain, and then stop or change to a different function with a new time domain. And you can have functions that turn on for all values of positive time, but you'll just have new functions that will turn on at certain time points. And you might have some functions that will turn off when another function will turn on. And the question is, how do you find the Laplace transform of that type of description? What we've done previously is find, based on the inverse Laplace transform, we've found what the discontinuous function will look like. Well, now we're going to do that in reverse and find, based on a function, what the discontinuous inverse Laplace transform will look like. So let's have a look at the first question here that we've got. So we've got a function f of t equals 4 between 0 and 2, and then 2t minus 3 for t is greater than 2. So let's just see roughly what that looks like. So between 0 and 2, the function is going to be 4. It looks something like that. And then for t is greater than 2, it's going to be 2t minus 3. So when t equals 2, 4 minus 3 is 1. So it's going to start at 1, and then it's going to have a gradient of 2. So 3 is going to be, so it's going to go something like that. And we can see there's a discontinuity here at 2. And that's 4. And that's going to be 1. Yeah, okay. So that's what our function looks like. And we want to find out the inverse transform of that function. So the first thing to do is to describe the entire function across the entire time domain. And we're going to be able to do that using the Heaviside step function. We're going to be able to say that the function turns on over here between 0 and 2. It's going to be 4. And then what we're going to do is turn the function off. And then we're just going to turn this function on for t is greater than 2. And that way we can build up a picture of the entire function, which should be a fairly easy way of doing that. And then we can just find the inverse Laplace transform of a series of Heaviside step functions using the principle of linearity, which we've seen before. So let's describe the function in terms of the Heaviside step. So we'll always start with ut. So when t equals 0, we're going to have ut dot 4, because 4 is the function between what starts at 0 and 2. And then what we're going to do at 2, we're going to turn the function off. We're going to turn this function off, 4. So we've got nothing, and that makes it easy to build up the whole function across the entire time domain. So then we're going to subtract at ut minus 2 dot 4. So that's going to turn that function off, now at 4. So for instance, if we were to draw that function there, I know this is probably very straightforward and obvious, but I'm going to do it anyway, just in case it isn't. So we've got f of t over here, and we've got t over here. So that description, ut.4 minus ut minus 2.4, is going to be, I'll do that in red. So that's going to be 0, 0, 0, 0, 0, and then it's going to turn on a value of 4, and then it's going to go on forever, but at t equals 2, we're going to subtract that function. So that is what that looks like, just what we've written over here, which is exactly this part over here. 0 for t is less than 0, and 4 between 0 and 2, and then 0 for t is greater than 2. So it's really, what it's really doing is, I know I'm kind of labouring over this point a lot, but I just want to make this very, very clear. It's kind of saying that we've got the first function, ut.4, is really saying this. It's going to go on forever, just like that. And then we've got another function of, when t is 2, dot 4, we've got like another function that looks like this. And then if we subtract from the blue line, we subtract the red line, you can see we're just going to be left with that bit in the middle, aren't we? Just that bit over there, kind of that. I hope that's clear. So now we're back to 0 over here. We can start building up this function. So we can say plus u t minus 2 dot 2t minus 3. So I'll just write that down over here again, just to make it a bit clearer. So f of t, we've got ut dot 4 minus ut minus 2 dot 4 plus ut minus 2 dot 2t minus 3. And remember that we can see some kind of a second shift theorem going on here, because we've got ut minus c dot the function t minus c. But it's not exactly t minus c. So the first thing we want to do is make sure that we get this into a nice, easy ut minus c dot t minus c type of expression. And then we can use the principle of the second shift theorem, which was the Laplace transform of t minus c dot f of t minus c equals e to the minus cs f of s, providing, of course, that the forward Laplace transform of f of t equals f of s. And do you remember before we, I'll tell you what, let's do that first. So we'll just rewrite that, saying f of t equals ut dot 4 minus ut minus 2 dot 4 plus ut minus 2 dot t minus 2. And I'm going to take out the 2 over here, so we get 2t, but then we end up with minus 4. We need it to be minus 3, so we just add a 1, just like that. Okay, and then I'm just going to expand this. So we end up with f of t equals u of t dot 4 minus t minus 2 dot 4 plus u t minus 2 t minus 2 dot 2 plus u t minus 2. So we can see we've got 4 ut minus 4 ut minus 2 plus 2 ut minus 2 t minus 2 plus ut minus 2. So you can see that we can actually collect the terms of ut minus 2 over here and minus 4 ut minus 2. So we can do that and then simplify the expression. So let's go ahead and do that. So we can say f of t equals 4 u of t and 1 minus 3. Is that right? Yeah, minus 4 u t minus 2 plus 1. Then we minus 3 dot u t minus 2 plus 2 u t minus 2 t minus 2. Now, all we have to do, remember on the principle of linearity, we can say that if we want to know what the Laplace transform of f of t is, of this entire expression, that's going to be identical to the Laplace transform of each individual component. So do you remember before we said that the Laplace transform of ut is going to be 1 on s? Yeah, because the Laplace transform of a is 1 on s. And multiplying the function by u of t doesn't change anything, because the definition of Laplace is defined over the semi-infinite integral between infinity and 0. And since that ut function is saying that, well, it's going to be 0 for less than t is 0, and then 1, multiply it by 1 for everything beyond that, up to infinity, the ut doesn't actually change the function, so it's going to be 1 on s. So if it was the Laplace transform of a ut, it would just be a on s. We also said that the Laplace transform of ut minus c equals e to the minus cs on s, because, do you remember, if we do the Laplace transform of ut minus c, e to the minus st dt, and ut minus c is just shifting this turn-on function to the value of c, wherever that is. And if we have the e to the minus st like that, all we're doing is taking the limits from infinity to c of e to the minus st dt. Okay, and that's just going to be minus 1 on s, e to the minus st evaluated between infinity and c, which is going to be minus 1 on s 0 minus e to the minus cs. Okay, whoops, sorry, can't see that there. And then that's just obviously going to be e to the minus cs on s. So that's just a little recap of why the Laplace transform of ut minus c is e to the minus cs on s. And obviously as well, that if we just plug in c equals 0, e to the naught on s is going to be 1 on s, which is what we have over here when c is 0. And we also know that the Laplace transform of ut minus c, f t minus c, is going to be e to the minus cs f of s, providing that the Laplace transform of f of t is f of s. So based on that, we can now actually perform the inverse transform of this function with hopefully quite a lot of ease. So we can say that f of s is going to be 4 on s, or 4.1 on s, minus 3 dot u of t minus 2. Well, that's just going to be e to the minus 2s on s, plus 2 e to the minus 2s f of s. So here, f of t is just going to be t, isn't it? Because the shift is incorporated into the function. So we can say that f of s in that case is just going to be, remember the transform, the Laplace transform of t to the n, is going to be n factorial on s to the n plus 1. So that's going to yield 1 on s squared, yeah? So it's going to be 2e to the minus 2s dot 1 on s squared. So just cleaning that up a little bit, we can say that f of s equals 4 on s minus 3e to the minus 2s on s plus 2e to the minus 2s on s squared. Okay, let's have a look at another question. So in this question we have f of t equals 6 between 0 and 1, 8 minus 2t between 1 and 3, and 4 for t greater than 3. So let's just draw a little scale here. So we've got 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. So we've got a sense of a scale now. So it's going to be 6 between 0 and 1. Something like that. And then between 1 and 3, it's going to be 8 minus 2t. Remember, always evaluate the function at the breakpoints. Don't just assume that 8 minus 2t is going to start where the previous function left off, because it doesn't have to be like that. With Laplace, you can have function discontinuities, how you pronounce it. So that the new function might begin here, it might begin here, it might be anywhere. So 8 minus 2 times 1 is 6, so yes, it will actually begin at 6 over here. And then at 3, it's going to be 8 minus 6, which is 2. So it's going to come down to 2 over here. And then for t is greater than 3, the function is going to be 4. So this is a good example of a function that's discontinuous. So it's going to be 4 like that. And that's obviously going to go on to infinity. So this is our function, and the question is, what's the Laplace transform of this discontinuous function? So the first stage is just to write out what we know in terms of the Heaviside step. So we can see at the beginning, we've got the function 6, which is turned on, so ut dot 6. And then when t equals 1, let's turn off that function, so we'll subtract ut minus 1 dot 6, which effectively is describing the function, a new function of 6 turning on only at 1, and we're subtracting the previous one from that, so we're left with this little bar in the middle. And now we can concentrate on the next part, so we can say plus ut minus 1, there's a function that turns on at ut minus 1, and that is 8 minus 2t. And that's going to go all the way until t equals 3, so we'll subtract ut minus 3, 8 minus 2t, and then we'll add at ut minus 3 the function of 4. So now let's do what we did previously. So we need to get this in the form of ut minus c dot f of t minus c, so that we can use the second shift theorem, which is the Laplace transform of ut minus c dot f of t minus c is e to the minus cs dot f of s, providing that the transform of f of t is f of s. And then we can use that in reverse to get the inverse. So let's just write this underneath. So we can say that's going to be 6 ut minus 6 ut minus 1 plus u t minus 1 dot, remember we have to have t minus 1 over here, and that's going to be dot minus 2, and that's going to, minus 2 times minus 1 is 2, so we need to add on 6 to get 8, and then we'll subtract ut minus 3 dot t minus 3, another minus 2 over here, and that's going to give minus 2, and that's going to give 6, so it has to be plus 2. Is that right? Minus 2 to minus 3, 6 plus 2 is 8, plus 4 dot ut minus 3. So let's simplify that. So you can say 6 ut minus 6 ut minus 1 plus ut minus 1. We can do a dot minus 2 over there, should have been. T minus 1. Oh, I've kind of mucked that one up. Didn't mean to. ut minus 1 dot minus 2 t minus 1 excuse me, ut minus 1, I'm going to do minus 2 dot ut minus 1, I was right the first time, t minus 1 plus 6 ut minus 1. That's right. Yeah, minus 2 ut minus 1 t minus 1 plus 6 ut minus 1. And then we'll have the minus, minus, so that's going to be plus 2 ut minus 3 t minus 3 minus 2 ut minus 3 plus 4 ut minus 3. Okay, I think that's right. So let's bring that down and tidy things up a little bit. So we've got 6 u of t minus 6 ut minus 1 minus 2 ut minus 1 t minus 1 plus 6 ut minus 1 plus 2 ut minus 3 minus 2 ut minus 3 plus 4 ut minus 3. So can we simplify anything here? We've got t minus 1, 6 ut minus 1, and 6 ut minus 1. So that's going to cancel. And we've got 4 ut minus 3. No, we can't do that. So I think we're going to be left with 6 u of t minus 2 u t minus 1 t minus 1 plus 2 u t minus 3 t minus 3. Oh, 1 minute. Have I done that right? 2 ut minus 3, 2 ut minus 3 that should be another t minus 3 over here, plus 2 ut minus 3 dot t minus 3 minus 2 ut minus 3 plus 4 ut minus 3. So we can actually simplify those two terms. We can say that's going to be equal to 6ut minus 2ut minus 1 t minus 1 plus 2ut minus 3 t minus 3 minus, plus 2ut minus 3. And that's going to be f of t. So, based on the fact that we can now say that the Laplace transform of ut is 1 on s, as we established before, and the Laplace transform of ut minus c is e to the minus cs on s, and the Laplace transform of ut minus c, f of t minus c, equals e to the minus cs f of s. We can now find the Laplace transform of the entire function. So we can say that f of s equals, that's going to be 6 on s, minus 2. I'm going to use this one, e to the minus 1s dot f of s, and that's going to be 1 on s squared, because the function is t. So if the function is t, the Laplace transform is going to be n factorial on s to the n plus 1. So that's going to be 1 on s squared plus 2 dot e to the minus 3s dot 1 on s squared again, plus 2 dot ut minus 3, so that's going to be e to the minus 3s on s, using this transform over here. So we can tidy this up a little bit, and we can now say that f of s is going to be 6 on s minus 2 e to the minus s on s squared plus 2e to the minus 3s on s squared plus 2e to the minus 3s on s. And that's our final answer. So we were able to find the Laplace transform of a discontinuous function that looks like that.